Hi, this is Mr. Kwang. I'll be covering direct current circuits. This is chapter 15 of our H2 physics syllabus. This is part 1. We'll be talking about circuit symbols and conservation laws. Alright, so this is a quick run through our learning outcomes for this chapter. We have quite a short chapter for this one. It will just be covered in 2 lectures, and a lot of the knowledge is you already learned them in undercurrent of electricity. Alright, so this is what we're going to talk about. Right, before we start, let's just have some guiding questions to help you take a different perspective of this chapter first. Right, so how are symbols and diagrams used to represent real circuits? How are the principles of charge and energy conservation applied to an analyzed circuits? So please keep these 2 questions in mind throughout this whole chapter. You will be revisiting especially the second one very, very often. Alright, so let's quickly jump on to our introduction. So DC circuits is essentially direct current circuits. Okay, it's a flow of charged particles in one unchanging direction. Right, and we know that circuits are means for conveying energy from one point to another, and it's also to convert energy from one form to another. So this converting energy from one form to another, you have learned it under current of electricity when you talk about potential difference. Right, and we also learned that charges cannot be destroyed. We cannot gain extra charges in the circuit, nor do we lose any of them. Okay, and for this chapter we'll be analyzing current and potential difference in circuits. Okay, so these 2 pictures here are the representation of your current. Alright, we have learned in chapter 14 COE that basically most of your charge carriers are electrons, and they travel from the negative end of the battery to the positive end of the battery. Alright, but we know that the conventional current we always consider to come out from the positive end and then re-enter the battery through the negative end. So for most of our analysis here, we'll be using the conventional current instead. Alright, but do bear in mind that the actual current is mostly made out of your electrons. They are traveling the opposite direction. Okay, so these are some of the circuit symbols that you should have seen before from your time in secondary school. Just want to highlight a few of them. Mostly here for DC, we're talking about cells and battery or cells. The difference between a cell and the battery or cells is basically a cell is a single energy component here. A battery or cells basically consists of multiple cells put together in series. Right, and AC supply, we'll talk about it in the next few chapters. Earth connection, switch, fuse. I think what is important here is that the wires connection here, if you see a dot here, that means they are joined. If you see this jump here, this is a cross, that means they are not connected. Right, filament lamp, fixed resistor, variable resistor where the resistance can be adjusted. Potential meter you learned in this chapter. LDR, thermistor in this chapter as well. Ammeter and voltmeter are quite standard to you guys. Okay, galvanometer is essentially a very sensitive ammeter. Basically, if there's a current going through, the galvanometer will show a deflection. So sometimes you see it represented as an upward arrow. Sometimes you see it represented as a letter G. Right, diode you have learned before in COE. LED is basically a diode that emits light. Alright, and some of the other things here are not so important. Right? Okay, so we're going to move on to conservation laws in DC circuits. Okay, we need to pay some tribute to this guy here, Gustav Robert Kirchoff. He was the one who came up with the 2 laws. We commonly call them Kirchoff's laws, but they are basically about the conservation of charge and conservation of energy. Alright. Okay, so let's move on to the first one, conservation of energy charges. Alright. Sorry, I think it should be electronic charges. Right. So in a complete circuit, the total current entering a junction is equal to the total current leaving the junction. So the sum of current entering is equal to the sum of current exiting the point. Okay, so this goes back to the idea that you cannot create or destroy charges, nor you allow it to accumulate at a point in the circuit. So if you look at this point X here, this junction X here, right, I have 2 currents that are coming in, I1 and I2 coming in. I have 2 currents that are going out, I3 and I4. So if I use this electron charges conservation to explain this, right, then it will be I1 plus I2 equals to I3 plus I4, right? Okay, so there's a checkpoint 1. What is current I? Okay, so if you look at this junction here, junction P, there are 2 currents entering, the 1 ampere current and the 2 ampere current. There are two currents exiting, I and 0.8 A, 0.8 ampere. So the total current entering is 1 plus 2. The total exiting is I plus 0.8. So the total current in I is just 3.0 minus 0.8. I get 2.2 ampere. Okay. Next, we move on to conservation of energy. Okay. In a complete circuit, the algebraic sum of the EMF is equal to the potential difference across all resistors, i.e. the total EMF must equal to the total potential drop. Alright, so once we have this, then we can analyze this again. Okay, due to conservation of energy in the system, total EMF must be equal to total potential drop of the circuit. Okay, so what this means is that remember your EMF are your sources of energy inside your circuit. Okay, the total energy provided by these two cells here must be equal to the total energy drop across these two resistors. Remember, the cells are converting potential energy, usually in the form of chemical potential energy, to electrical energy. Okay, and the amount of energy they convert, right, will be the amount of electrical energy they provided will be dissipated across these two resistors. All right, R1 and there's missing R2 here. So the total energy dropped by these two must be equal to the total energy provided by E1 and E2. All right, so if we look at the power equation, so E1 times I, because this is a series circuit, right? So there's only one current I going through this. So the power generated by sources E1I plus E2I is equal to the total power dissipated by the resistors V1I plus V2I. And then we can cancel with the current, and then we get E1 plus E2 equals to V1 plus V2. So in a single loop like this, right, your total EMF must equal to your total potential drop. Okay, so let's look at this simple example. This is extracted from FET physics. All right, we have two EMF sources here, 4 volt and 9 volt, and I connected it to two resistors over here. What I've done is that I've tapped 2 voltmeters across it, and you can see that in the first case, your total EMF is 4 volts plus 9 volts. You get a total of 13 volts. And if you check the two numbers at the bottom, the two potential drops across your two resistors here, right? It's also 8.67 plus 4.33. That'll give you 13 volts of drop. Okay, this is assuming the cell has no internal resistance, of course, and the wires have no internal resistance. Okay, next we have this setup here, which looks very similar, but then if you look carefully, your cells are connected in the opposite direction. So the 4 volt one is flipped around. So in this case here, right, the total EMF provided by this in this loop is equals to 9 plus negative 4. I get 5.0 volts of EMF. Okay, and in this case here, my voltage, my potential drop across the two cells is also 3.33 and 1.67. So that will give me a total drop of 5.0 volts as well. All right. Okay, this is the end of this part. We will do the discussion for the next part very soon. You can just move on the rest of your SOS package for now.